So now I will introduce our speaker. My name is Daniel, and it gives me immense pleasure to introduce Andrew Nelson, which is a young plasma researcher currently completing his PhD work at Princeton University. He received his undergraduate degree in engineering physics from the University of Colorado Boulder, where he conducted research in dusty plasma diagnostic and was designated as the outstanding graduate of the college in 2016. Auk currently works on pedestal-related experiments at the D3D and Kirstar tokamaks and is using multi-phase approach to understand the relationship between pedestal, core, and scrape-off layer dynamics. He hopes to continue fusion research after graduate school with a focus on teaching and education, as he will do today. Without further delay, I will now mute myself and hand over to him. Welcome everyone and enjoy the talk.
Thanks, Daniel. That's a very nice introduction. I'll share my screen here and we'll get started. All right, cool. Well, welcome everyone. Today I'm going to be talking a bit about an overview introduction to H-mode. This is really geared as an introductory talk, specifically focusing on ELMs and ELM-free regimes. So tokamak plasmas are generally plotted in such a toroidal cross-section, a poloidal cross-section such as this. And if you look at how the heat flows from these plasmas, it's going to be very hot in the center, and it will flow outwards through the plasma until it reaches this white line, the thick white line here, which is called the separatrix. And from the separatrix, it will flow through the scrape-off layer, where these dashed lines are, towards the diverter. And if we look at like typical temperatures for a tokamak reactor, you'll see that the core is super, super, super hot, well over the temperature of a star. The edge is still very hot, and then by the time it gets to the wall here, it has to reach room temperature. So you have this incredible temperature gradient that goes from the core to the wall. And that's really the subject of the talk today, is what makes that pedestal and what are the different phenomena associated with it. So this temperature gradient, as you can see here, I've plotted in orange H mode. There's a strong temperature gradient right in the edge region, and it's associated with an ETB, which means edge transport barrier. We often call this a pedestal region. There's another mode that tokamaks are often run in, which is called L mode, that doesn't feature this steep gradient region as much. And so the difference between L mode and H mode is the formation of this edge transport barrier right at the edge. If we think about what this means in terms of how the different regimes are formed, L mode, like I said before, is a low confinement mode, where we just turn on some faucet or some heating source, right? And that heating source is going to just in steady state, everything goes in, has to come out, and so it will run straight to the wall, the machine wall. When we go into high mode or H mode, we introduce some bifurcation to the system. And this is the bifurcation I'll be talking about. I've depicted it here as a bucket. But basically, it's just a transport barrier. So just like the bucket stops the water from flowing down, the transport barrier is going to stop the plasma temporarily from flowing out from the core plasma to the machine walls. So with that little introduction, here's an outline of the talk. We're gonna do a better introduction to the H-mode pedestal, why it's important, what it is, and then we'll talk a bit about ELMs, and I'll explain what ELMs are later. And then moving on, I'll do a brief characterization of H-modes and small ELMs and ELM-free regimes. And so that's how this will go. So starting with the introduction to the H-mode pedestal, why do we care about this pedestal? Well, pedestal actually turns out to be super important, and it's likely that fusion performance will rest upon the pedestal. In this plot here on the right, I've shown the P fusion, the fusion power, as a function of beta ped, which is really just a measure of how strong your pedestal is. And as your pedestal gets stronger, your fusion power increases until we get to a regime where we might have burning plasma physics. So in order to get to a burning plasma reactor, we need to have a good pedestal, and thus it's important to understand how the pedestal behaves. So what are some trademarks, phenomenological trademarks of a pedestal? Well, like I said before, right, we have the steep gradient region right in the edge, and we also have a ER well dip. And so this dip in the ER is literally just a well in the electric field. And this well in the electric field turns out to be very important for the development of the steep gradient region. And why is that? Well, in the edge of the plasma, we're going to have a bunch of turbulence. And these turbulence is going to form large eddies. And if the eddies are large, you'll have a lot of turbulence, and that flushes out your plasma. But if you have a deep enough ER well, because there's shear in the ER, you actually start to decorrelate these eddies. You start to rip apart these eddies and make them into smaller eddies. Smaller eddies are associated with reduced transport, and thus you start to build up an edge transport barrier that allows you to build up steep gradients in this region. Yeah. So again, this is the pedestal. It's a steep gradient region, and it's associated with the transport barrier that we get through decorrelation of turbulent eddies with the ER mode. The pedestal turns out to be pretty complicated, and I don't have time here to do a full investigation of everything that goes on in the pedestal and everything that makes it complicated. So I'll just highlight a couple things that I think are interesting. For example, most tokamaks today are filled with gas, but on ITER, because of the opaque scrape-off layer, we're going to need to do fueling through pellet injection. And so on the plot on the left here, you can see the line average density every time a pellet goes in. There's this big yellow spike, and it fades to purple after the pellet. And if we look at how the pedestal behaves to that, you can see a big change in the pedestal right after the pellet comes in. You have this big yellow spike. You also see a dip in the temperature pedestal, as opposed to like the normal pedestal, which might be in purple here. And so this has strong effect on the pedestal, and by changing the pedestal, you can change the stability of the plasma and a bunch of other things. So it's important to understand how stuff like this works. Another sensitivity that is on the pedestal is on the scrape-off layer diverter structure. So in these plots here, I've plotted two different pedestals for very similar discharges, but we've changed the diverter structure. So the top plot has an open diverter, and the bottom plot has a closed diverter. And this just refers to how much the shape of the diverter itself is closed like a box to prevent neutrals from the diverter from going back up into the plasma. And just by changing the shape of the diverter, not by changing the core plasma at all, you can see we have very different pedestal structures. While the pressure pedestals in both these, the green lines, might be fairly similar, the density and the temperature pedestals, blue and red, are quite different between the open diverter case and the closed diverter case. So there are lots of sensitivities on the pedestal, and it's a complicated region that we have to understand. Unfortunately, it's very difficult to understand the pedestal for a bunch of regions, and one of the reasons for this is it's difficult to diagnose. The pedestal around the very outside of the tokamak here is a very small layer. It's order centimeters, and it has super intense temperature and density gradients. And so you have big changes in your plasma parameters over a small period of time, or a small period of space. And due to this, you need really sensitive diagnostics. I've shown some on Aztecs and D3D here, where you have like clustering of diagnostics right around this scrape-off layer region. And it turns out that it's difficult to measure this, and there's a lot of work being done. But we're getting better and better with these diagnostics. And with better diagnostics, we can apply better theories and better understand how the pedestal works. So, quick summary of that introduction. The edge transport barrier that we talked about before that is responsible for H-mode is formed by a pedestal, and it is responsible for the increased performance that we see in H-mode. So if we look at our diagram here, in H-mode, we have the faucet going on a lot. We have this bifurcation, this bucket, which is representative of the pedestal, that is forming some sort of transport barrier to keep the plasma from hitting our machine walls, the hot plasma from hitting our walls. So moving on, let's talk a little bit about ELMs. So, right, we have this bucket, and if we thought about this bucket in real life, what would happen if you turned on a faucet and held a bucket under it? Eventually, the bucket would overflow. And this event is called, in tokamaks, an ELM event. It stands for Edge Localized Mode. And it's really an instantaneous, very quick burst of plasma that hits your machine walls. And when this quick burst happens, you can think of this kind of like a high-pressure water gun hitting your brick wall. Suddenly, it's going to do a lot of damage to your machine walls, and so it's definitely something to pay attention to. There are a lot of great videos of ELMs out there. This one is from MAST. You can see the plasma is in this general steady state, and then it flashes really quickly. I'll try to stop it when it flashes. And this flash, right, this flash is an ELM event. So you can see the core plasma is kind of being connected right to the walls. We get a bunch of light because we have this hot plasma hitting the machine walls and producing a bunch of radiation in the neutrals around that region. And So these ELM events can happen over and over and over again in your H-mode plasmas throughout your entire discharge, and they're very associated with instabilities in your discharge as well. So why do we really care about these ELMs? Can't we just let the bucket overflow every once in a while? And the answer is probably not. ELMs can be very damaging to the machine walls. In this graph here, we have E target, or epsilon target, which is the peak ELM density, energy density at the target. And on the right, we have plasma current. And as we ramp up plasma current, we can see in this green scaling here that the peak ELM target density is actually going to increase and increase and increase. Also plotted on this are two things, two limits really, which are limits for toroidal gap edge melting and limits for surface melting of your diverter. So if you want to have ELMs in your plasma, you're going to have to avoid these limits, otherwise you're just going to melt your machine's walls at 15 megaamps, which is nominally where ITER is supposed to operate. And based on this scaling here, we'd expect we need like a W ELM over W plasma to be about 0.1%, which is really down here, very low. And that's not really seen too often in today's machines. Usually ELMs are much larger than that. And so ELMs are definitely a problem in that they might melt our machine walls, and something to look forward to. So if we want to be able to control them, we have to understand them. And one way to do that is to derive them from MHD. So if you're familiar with MHD, you might be familiar with this equation. If you're not, don't worry about it. This is delta W. It's really just a change in energy. And if due to some instability or motion in your plasma, and if your terms are positive, then that instability won't happen. It'll be a stable instability. If your terms are negative, then your instability is going to happen, and it's going to be an unstable event in your plasma. And so you can see here, and there's a bunch of terms in this equation. I'll just highlight two at the end of terms 4 and 5. Term 4 is a term that's built on the pressure gradient, delta P naught here. And term 5 is a term that's built on the current here, delta J parallel. And so we have a pressure-driven mode and a current-driven mode that are driving our instabilities unstable. And it turns out that we can actually work through this and apply it to a tokamak geometry. And we end up with coupling between what we call peeling and ballooning modes, current-driven and pressure-driven modes, that are responsible for these type I ELMs. So the ballooning mode is destabilized by grad P, like I said before. It's stabilized by current. The peeling mode is the opposite. It's stabilized by grad P, but it's destabilized by J. So if we plot the state of our plasma as a function of the pressure gradient, right, grad P, and the edge current, J, we see that we have this stable regime. And then if we go too high in the current, we run into a peeling mode. If we go too high in the pressure, we run into a ballooning mode. And if we go too high out towards this peak here, we actually get coupling between them to peeling, ballooning, unstable. And H-mode plasmas are going to exist right where this black error bar is. So this is an experimental measurement. And the H-mode plasma sits right on the boundary of this this border. And so it's going to be ELMing. It's continually going into the peeling region and outside of it. And then these two white things are RMP. They're ELM-free. And we'll talk about those later at the end of the presentation. So what does an ELM look like? Again, we have this instability boundary, right? We have a stable region and an unstable region. If our current and our pressure gradient are rising between the ELMs, eventually we're going to hit an unstable region, and that triggers an ELM crash. When the ELM crashes, a bunch of the plasma gets spewed out into the scrape-off layer, and our pressure gradients drop, our current densities drop, and we recover back in the stable region. And so we're really just doing circles along this instability boundary during a typical type I ELM cycle. And this is why we get this repetitive flashing on of instabilities on and off. We can actually use this information to learn more about a pedestal as well, because the peeling ballooning modes form a constraint that we can use to constrain our pedestal width and our pedestal height. So in these two plots, again, we have the pedestal width and the pedestal height. I've plotted the blue line here is the peeling ballooning constraint that we just talked about. Turns out there's another constraint that was developed by Phil Snyder in the EPED model, which is the kinetic ballooning mode constraint, which is this dashed green line. And this is kind of a soft constraint that just limits your pedestal height growth, but you can still grow along this line as you go. If you take experimental measurements, you'll find you really end up right at the intersection between these two constraints. And so the theory is that during an ELM cycle, we'll have an ELM crash that will reduce our pedestal width, reduce our pedestal height, limit our pedestal, and then we'll recover until we hit one constraint, and then recover again until we hit another constraint. And as soon as we hit this big global peeling ballooning constraint, we have another ELM. And so we're cycling back and forth. This gives us some sort of predictive measure for how our pedestals work. I just talked about Type I ELMs. There are many other types of ELMs. You can see here 3 different machines plotted: Aztec, GAT60U, and JET, clustered by color, but also these different symbols are clustered by types. So here we have some grassy ELMs, which we didn't talk about. These red X's are the Type I ELMs of J360U. These squares might be Type III ELMs. And so in collisionality and beta P space, there's different types of ELMs. And some of these ELMs have more favorable scalings than others. Towards the end of this presentation, we'll talk about I mode and QH mode. We actually don't have any ELMs at all, but they're still improved confinement regimes. And so that's something that we definitely want to look forward to as we move towards a burning reactor. So a quick study, or a quick overview of ELMs, right? Peeling ballooning MHD instabilities, called ELMs, limit the pedestal. They flush impurities, which is great. I didn't talk about this, but they actually take impurities like tungsten and flush it out of the plasma so that we can avoid over-radiating inside. So that's a good thing about ELMs. But unfortunately, they create high heat fluxes on PFCs. And this is really damaging to machine walls and very much a limit on how many ELMs we can tolerate in future reactors. So again, our diagram here, we're filling up the bucket. The bucket reaches, has much plasma as it can store, and it pours out into the machine walls. And this is worse than the ELM mode, where we're just drizzling on the walls, because we have this concentrated stream of energy. That's actually, if you think about like a water gun, you can bore through steel or a brick with a water gun, but steel and brick are both fine in rain. So we have this concentrated peak of energy, which is actually able to melt the machine walls, and that definitely has to be looked at. So in the interest of time, I'm going to try to combine the next two sections a little bit. We'll talk a little bit about characterization of H-modes, and then move on to small ELM or ELM-free regimes that will be really good for future reactors. This is a fantastic diagram that I stole from Dr. Lochner, which basically shows a bunch of different tokamaks over the years, right? So we started with these tiny tokamaks, and we're moving to something really big, ITER, demo. Not shown here are things like CEFTR, FNSF, Spark, maybe ARC. And as we move forward, there's a bunch of stuff to look at. And it turns out, as you might imagine, if we have this many different types of tokamaks, of course, we might have a bunch of different H-modes as well. And it turns out there are almost as many types of H-modes. Here's a presentation that was given to D3D back in 2016 of just the different types of H-modes in the D3D tokamak. And as you can imagine, changing tokamaks, you might change these parameters a little bit. We don't have time to go into all of these today. So what I want to do is really focus on what we need to do for future reactors in order to make them applicable to a burning plasma regime. And like we said before, right, in H-mode, the ELM confinement's too good and we spill over the top. So the solution might be to move towards an ELM-free regime. And you can think of this as kind of poking holes in our transport barrier. So if the bucket, we poke holes and little bits of water can leak out, and thus we don't get this intense stream of water that hits our bricks. And so we'll talk a little bit about ELM-free regimes in the remainder of this presentation. If we look again, we had a plot like this earlier, right? Collisionality on the x-axis, and this time it's delta W ELM over W ped, which is really just a measure of how big the ELMs are on the y-axis. Type I ELMs, which is the theory we gave above, and like the standard type of ELM, are all very big ELMs spanning over a large range of collisionality. But it turns out the other types of ELMs that I mentioned earlier are much smaller, and sometimes there's even no ELMs, like an I mode or QH mode or EDAH mode. These types of modes are definitely things we want to look at for ITER and for demo and for future reactors. Because they prevent tungsten accumulation, they still are ELMs, they still are able to flush impurities out of the main plasma, but they're small enough that they might not hurt our machine walls. So it turns out, of course, as you might expect, there are another zoo of ELM-free techniques. And this is another presentation with a bunch of different ELM-free techniques. We won't focus on all of these, but I want to talk a bit about why, or what makes an ELM-free technique relevant. So this was a slide that I stole from Max Stenson-Marker at the ITER International School last year. And it's basically just comparing 4 different types of ELM-free regimes, or small ELM regimes: pellet pacing, I mode, QH mode, WPQH mode. I'll explain these acronyms later. But to reach actual application on our device, we have to meet a bunch of criteria. And so these criteria are things like being compatible with high confinement, being able to be accessed in low torque regimes or low collisionality regimes where we expect either to be, being compatible with radiated diverters or with fueling and pumping systems that will be used on future machines, and also being compatible with PI and J, close to the injected power, close to the LH threshold, close to low LH threshold, and compatible with high Z PFCs. And for these three, Max Fenstermacher went through and labeled the state of the research. Is this technique compatible with these conditions? You can see there's a lot of yeses on here, but there's also a couple no's and very many question marks. So there's still a bunch of research to be done if we can actually apply these regimes to burning plasma techniques. Omitted from this table are a bunch of different other techniques. Right? We talked about a whole slew before. Among them, promising, I think, are RMPs, resonant magnetic perturbations, which we'll talk about later in this talk, and grassy ELMs, which are a big focus on CEFTR at the moment, which are very, very small ELMs at high Q95 that don't have too much effect on the wall of the plasma. So I'm just going to go through a couple of these regimes to try to give you a little picture about how they work and how we're actually poking holes in the bucket to make this happen. So I mode, which is an intermediate regime between L mode and H mode, can be thought of basically by separating the energy barrier, which is your temperature barrier, and a particle no barrier transport. So we have H mode temperature-like and L mode particle-like, and because of this, we don't actually get ELMs. We have additional transport through our pedestal. It has good energy confinement close to H mode, which may be favorable for power scalings in future regimes, and you can get it with unfavorable BT at high BT. So this is a very common regime at CMOD, which operated at really high BT. Issues are you really need that high BT to get there, and you also have to control your plasma so much that it doesn't increase the confinement and actually reach the H mode. Because if you have too good of an I mode, it turns into an H mode, and then you start hurting your plasma walls. So what does I mode look like? We have high particle transport, which prevents the formation of an NE pedestal, right? So we have a TE pedestal, but not an NE pedestal. And you can see in this graph, we are moving on a discharge from L mode, this white region, to I mode in this middle region, to H mode, finally, in this top region. In H mode, there are no fluctuations here. So these density fluctuations that I'm showing are a indicator of the amount of density transport in our plasma. In H mode, there's very little, right? We have a big transport barrier that's preventing transport from going through. In L mode, we have a lot of transport. And in I mode, we start to shift how this transport regime is going. So we move to higher frequencies. We move to this weakly coherent mode that we have. So we have basically like an additional source of transport that is propagating through our plasma. But if you look at the integrated density down here, the I mode density is still much higher than the L mode density. So we still have improved confinement over L mode. If we want to look at this in terms of our pressure gradient and current gradient stability diagram like before, remember the H mode is right here on the nose of this stability diagram, where this is stable, this is unstable. And so H mode is right here. I mode, because of its doesn't have a density pedestal, is actually much lower. It's in the stable region. And because it's in the stable region, it's not forming ELMs. And thus we don't have to worry too much about the high peak heat fluxes that we get from ELMs. QH mode is another type of H mode-like thing that doesn't have ELMs and still has good confinement. So Q in this case stands for quiescent, which just means quiet. It's not ELMy. And in this case, we're eliminating ELMs by some sort of plasma self-organization that has to do with MHD activity in the pedestal. And we call this an EHO, which stands for edge harmonic oscillation. And this prevents pedestal growth from growing to the hard stability limits that we saw before with our peeling ballooning modes. In order to get QH mode, you have to have enough edge shear to drive those turbulent eddies apart, but you still have to be in low collisionality and in the kink peeling pedestal. And so one of the issues of getting this is getting large shear generation at low import torque. And there's some tricks people are using to play with this, like NTV torque generation. And this is definitely an open area of research currently. So again, we can look at this in terms of what type of transport does it produce, and what are the stability diagrams like. So in this case, I'll start with stability diagrams. Alpha here is the pressure gradient. J is here on the y-axis, same diagram you've seen before. Again, we're not really on this unstable region, which might curve down over here somewhere, but we're inside our stable region, and so we're not in an element regime. And the way we're doing this again is by producing extra turbulence in our pedestal. So here, instead of showing density fluctuations, I'm showing magnetic fluctuations. And these two regimes with these bright colored bands on either side are the EHO or QH mode regimes. So the way this experiment was run is if we slightly reduce the torque starting in QH mode, eventually we get to too low of torque, where we start to enter our high ELMing regime again. And then if we increase the torque, once that happens, we'll reach QH mode and we'll regain these extra turbulent modes forming in our pedestal. And so this shows that strong edge rotation is required for the edge harmonic oscillation, and thus required for QH mode as well. So again, we're introducing extra transport, we're poking holes in our bucket in order to avoid the ELM problem. The final technique I want to talk about briefly is resonant magnetic perturbations, RMPs. In this case, again, we're eliminating ELMs, and we're doing so by inducing additional transport through the application of non-axisymmetric 3D magnetic fields. So we're actually putting in additional magnetic fields to our plasma equilibrium in order to induce transport through the edge region. In this case, we get there, operation actuators are control coils. So we need external coils to induce this 3D coil, sorry. And it also has to be a very specific plasma shape and Q95. Issues are getting to this very potentially narrow Q95 window. And it turns out that if your coils on the outside are too strong, you actually run into locked modes, which are a source of disruptions. And that can be even worse than ELM events. And so you have to be very careful with how much RMP you actually apply. So what do these 3D coils look like? Here's an example in the D3D tokamak, which is shown here. The plasma is inside this red region. And on the outside, there's two sets of coils. There's inner coils, which are shaded in this diagram. And they go red, or positive, negative, positive, negative, positive, negative, as you go around the tokamak. So this would be like an N=3 setup. On the outside, in this diagram, they've shown more coils, and these are just positive and then negative. So this would be an N=1 configuration on the outside. And so by turning on these coils, you're actually able to do non-axisymmetric magnetic fields, which have a non-axisymmetric response in your plasma. So in this case, we're looking at the plasma, and you can see that the plasma itself has a response that's non-axisymmetric. And because it's non-axisymmetric, it's actually inducing extra transport through your edge region. This can give complicated suppression windows. So on the left here, we have a diagram which is labeled in poloidal angle here, which corresponds to the phase of your RMP. So that was the phase of the 3D perturbation you're applying. And from the middle here to the outside is the strength of the RMP. So this is 1, 2, 3, 4 kiloamps as we move outwards. And there's a bunch of different colors here. The colors in red represent places where we think the plasma would be a locked mode. The colors in green are just normal plasma behavior, and the colors in blue are where you get RMP ELM suppression. And so in this experiment, they basically just tried to plot out this diagram. You can see we start with these ELMs. These spikes here are measures of the ELMs, which are just really big spikes in the current in the D alpha as the ELM happens. And then the red line here is slowly ramping up the RMP current until we get to a certain regime. And you can see each one of these corresponds to a different plot here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And for these different regimes, depending on the phasing and depending on the amplitude, eventually you'll reach some regime where the ELMs disappear. So you have this smooth regime at the end. If you continue to increase your RMP current, eventually you get too high, and you actually end up at this red line, or these red crosses, which is when you get a locked mode and the plasma disrupts. So it's really a small window here where this is working, and there's more research being done to figure out the exact parameters of that window and how to control it. So a quick summary of ELM-free regimes, right? By inducing additional transport across the pedestal, we can suppress or mitigate ELMs. And you can think about this as basically inducing extra transport, poking holes in your transport barrier so that some of the plasma can flow out to the machine walls without producing really strong effects. So summary, it's all about buckets. It's all about transport barriers. If we start in ELM mode, we don't have enough plasma, or we don't have a hot enough and dense enough plasma to actually meet fusion requirements. And so we need to do something to that ELM mode. Likely, that will be the introduction of some transport barrier, some edge transport barrier, some pedestal, which is a bifurcation in our system that creates a transport barrier in the edge and prevents a buildup, or it allows for a buildup of higher temperatures and densities inside the core. However, such a transport barrier very often will have ELMs, which are destructive instabilities where a strong stream of splashed water or plasma moves out into machine walls and damages your machine walls. And so an answer to that is to have your transport barrier, but to not have it quite so strong. Induce additional transport across it so that you never reach the global limit set by peeling ballooning modes that creates an ELM, and then instead are just able to maintain a transport barrier with a slightly reduced limit. Yeah, so that's all I have. I was told it'd be nice to put opportunities to get involved into this presentation. And so depending on where you are in your education, if you'd like to work at PPPL, there's a bunch of different opportunities for you. There's a great undergraduate program called PPPL SULI. Of course, there's a graduate school at Princeton, and postgraduate work to early career scientist, to director of a laboratory, wherever you are there, there's careers available at this link. Great, so thank you very much. I think there's questions available, but I'll just leave a bonus slide up while we take them in case you want to do reading instead of listening.
Okay, thank you so much, Oak, for an amazing talk and also available for everyone. Everything is about buckets in the end, so I think we can
Everything is
start
about buckets.
the question and answer part. Manolis has one question already.
Okay, can you hear me?
Yes,
Yes,
I can,
Manolis,
thanks.
you can go ahead.
Perfect. First of all, Oak, thanks a lot for the presentation. It was quite interesting. So that's really important. I have a question. You frequently say that one of the, maybe not benefits, but one of the good things that we get by ELMs is that we are actually managing to remove impurities tungsten from the plasma. Considering though that our plasmas are mainly made from hydrogen, we have hydrogen plasmas, which is actually the fuel of our reactor. My question is, how much, what is the percentage of the impurities that we manage to move out? Don't we remove from the plasma with the ELMs mostly fuel, mostly hydrogen?
Right, so that's a great question. You're totally right that the plasma is predominantly made from hydrogen, deuterium, tritium, depending on what your machine is using. Small amounts of impurities, though, whether they're coming from the walls, whether they're put there by an experimentalist, can actually induce a lot of radiation in the core of the plasma. And this leads to something called like a radiative energy loss disruption. So one concern for ITER might be a speck of tungsten falling off the top of the plasma. And since tungsten has such a higher Z material than hydrogen, if that falls into the plasma, that tungsten will radiate a ton, and that can kill the plasma energy and cause a disruption. So even though we're mostly hydrogen and helium, or sorry, mostly hydrogen and deuterium, tritium, we still have to worry about getting impurities out of our plasma. And then another aspect of this is once we move to a burning plasma regime, we'll actually be creating helium ash. And so the tritium and the deuterium will form together. Of course, we make helium. And the helium now is in our plasma. It's not doing anything, so we want to get that out to have a pure plasma again. So I think your question was how much of the impurities do we actually remove with ELMs versus how much is it just like deuterium and hydrogen? And that depends a lot on the type of ELM you have and a lot on the type of plasma you have. If you have, I mean, predominantly you're going to have hydrogen and deuterium and tritium in your plasma, and so most of the particles that are flushed out with ELMs will be indeed hydrogen, deuterium, and tritium. But it still is an extra way to get impurities out of the plasma. So if you have some small percentage of tungsten, you need to keep that from building up and moving to the core. And one way to do that is through like impurity transport at the edge, which is helped by ELMs. There are other ways to do it as well. But ELMs can definitely help mitigate the impurity fluxes that you have.
Can I have a follow-up? Of course, if I am not taking the questions of others.
Please, yeah.
Then in this case, from which part exactly of the plasma is mostly this material removed, from the core or from the edge? Because ELMs are happening mainly to the pedestal and the edge of the plasma, so I would expect that this is from where your material would be removed, no?
Right, so directly you have, so when an ELM forms, you might remember back to the diagram that we had earlier, or sorry, the video I showed of MAST, you have these like arcing little streaks of plasma that kind of connect inside the separatrix above the pedestal to the scrape off layer. So it's almost like a fire tube from like your core plasma to your wall. You're right that most of the disturbance that happens during an ELM event is right in the edge region. It's right in the pedestal region. But it still is able to create transport through the core. If you think about like, if you have some distribution of tungsten, right, and you take a bunch of your tungsten out the edge, some of your tungsten might start to try to go from the core towards the edge to fill up that gap. So you can keep tungsten from going from the edge back to the pedestal region. And so by like flushing it out of the edge, you're also sort of in a slower way also cleaning it out from the core, if that makes sense.
Yeah, of course. Actually, yeah. Thank you very much for this.
Yeah. Thank you, Manolis, for a very interesting question. And I want to remind you guys that there are multiple methods to ask question. You can write it in the chat. You can raise your hand. Maybe this one is better because I can unmute yourselves, so you can ask more question and make sure that everything was clear for you. Now we have a question from Clara Bogar.
Yeah, thank you for your talk. I have two questions which are connected. So the question is, you mentioned the experiment with the changing of the torque by the modifying of the beams. And the question is, if you modified the power of the beam injected and then the torque, or if you keep the power constant and you modified the sources having, I don't know, counter one of them.
Right. So there's different ways to do it. In that experiment that I showed, they kept the power constant and were modifying the torque. Of course, you could also think of just like turning down your beam and that would change the power. On machines like ITER, we're going to be a little bit limited in this regime because there's not a lot of NBI torque available in ITER. So one of the things with QH mode that people are working on is finding extra ways to induce that shear at the edge without necessarily driving it directly from NBI torque. And so there's a couple tricks that people are playing along those lines as well.
Yeah, and the connected question is, can you decouple the impact of the presence of the fast ions and the torque on the pedestal?
I think people can. I don't know the results of that study myself, but I have seen studies specifically looking at fast ions in the pedestal region, and I believe yes, you're able to decouple the torque generation and the fast ion generation because you're keeping kind of your NBI power constant while you're doing this, and yeah, and so there's studies along that lines. Like I said before, a lot of these ELM-free regimes are still very much open areas of research. And so there's a bunch of research that needs to be done in order to figure out if these will be applicable for future regimes as well.
Okay, thank you.
Yeah.
Okay, we also have a question now from the chat from Maxim. What happens to poloidal and toroidal plasma rotation during RMP suppression? Does it affect radial electric field either?
So yeah, so RMP suppression does affect the plasma. It turns out that the biggest, I'll say the biggest noticeable effect in the experiments is something called density pump out. And so when you turn on your RMPs, the biggest effect you see is due to the additional transport, you actually lose some density and you lose some beta. And so you're actually diminishing the strength of your plasma as well. And that's kind of a common theme with these ELM-free regimes, that we reduce the strength of our H-mode a little bit in order to run away from the peeling ballooning constraint.
Okay, now I see a hand raise from Matthew.
Hello, thank you very much for the interesting talk. I wanted to ask about the origin of the well in the radial electric field that you mentioned.
Right.
I've heard before that to initiate the H mode, there's a critical threshold of heating power. I was wondering how this was related to sort of the criteria of the H mode initiating, and then the requirements or the characteristic feature of this formation of the well.
Yeah, that's a great question. So I didn't talk about the LH transition at all in this presentation. And part of that was because of time, and part of that was on purpose because it's very complicated. This is a slide from Ahmed Diallo. It kind of talks about the LH transition, and you get a good idea just by looking at it, a bunch of different things that might actually lead to the development of this ER well. That being said, there's a couple things that I think are important to know. So first, the ER well itself is coming from, well, I mean, it's partially responsible, right, for the shear we see in the pedestal, and that comes from some gradients drive and which creates shear flow, which then creates our ER well, which we can drive that way. So the ER well itself is a direct consequence kind of the pedestal. The question of how do we get to the pedestal is a complicated question. And like you said, there is always a critical power that you have to reach, a PLH. And so if you're below this power input, you won't be in H mode. And if you reach this power input, eventually you'll reach this bifurcation and you'll turn into an H mode plasma. And ITER, just for context, will be marginally right above this LH transition based on our current scaling. So we have just enough input power to make it over the PLH transition and to make it into H mode. There's a lot of work being done to study why this transition happens. And it's still very much an open question. But one of the leading explanations that I've seen to date is that we start off by generating a little bit of this gradient drive, and that helps generate our ER. But then we actually turn over to Reynolds work, which is just like a turbulence work that actually helps to build up and build up and build up this anisotropy and the pressure gradient. And so you end up with this this Reynolds work, which creates turbulence and zonal flows and more shearing. And more shearing then feeds back into higher pedestals, which feeds back into more ER. And there's this kind of predator and prey model until you actually end up with the final pedestal. So it's a complicated subject, and there's a bunch going on there. And it's definitely an open area of research. I think just recently, in the past couple of years or so, people have been able to reproduce what looks like an LH transition in gyrokinetic models, which is a big step forward in terms of understanding exactly how that happens. So did that answer your question?
Yes, thank you very much. I mean, it's clear that it's an incredibly complex phenomenon. But yes, it's wonderful to know that there's so much interesting physics to sort of investigate. Thank you.
Yeah, great.
Thank you so much, Matthew, for a very interesting question. Now I will go with Jalaluddin.
Great, thanks. Thank you, Oak, for the crash course.
Yeah.
So here in the ELM is the temperature and density crash in the pedestal region, right? So I have a couple questions related to that. First, are the timescales of the temperature and density profile recovery the same, or is one on a diffusive timescale and one on a transport timescale?
Yeah, that's a great question. This is again an active area of research, but Florian Logner has a bunch of great papers out about this, where you actually see the density and the temperature gradients recover on different timescales. So the density gradient usually recovers first, and then the temperature gradient recovers after that, along with the pressure gradient. And so you do have different recovery timescales of these two different gradients, temperature, density, and temperature. And the timescales of these gradients are related to inputs, and they're also related to what type of instabilities might cause to limit the gradients. So there's other, besides the kinetic ballooning mode, which I talked about earlier, there's other instabilities that might limit your pedestal, including things like the micro tearing mode or electron turbulent gradient, stuff like that. And these all have different effects, whether it's on your temperature gradient or your density gradient. Depending on which ones you trigger, you might have slightly different clamping times. But generally, your density gradients are going to recover first, and then your temperature gradient will recover second.
Right. Okay. Interesting. And the second question is, I guess, to what extent do ELMs affect the profile's ability to penetrate into the core? So, like, okay, this mode is edge localized, right? And you know, this crash is going to result in the pedestal being removed, essentially. But to what effect, or to what extent does, for example, the temperature profile drop beyond just the edge? Does it penetrate into the core?
Yeah, so that's a good question. I don't have a slide for this, but if you look at studies from Phil Snyder on the elite model and the EPED model, you'll see that there's a model basically for how far in the ELM actually penetrates. And each one of these ballooning and peeling modes that we trigger is going to have like a different radial extent. And so the ballooning modes might be farther in if they're higher n number. So if you hit the, let me just, for the sake of having a diagram up, we'll go back to this. So if you hit the edge of this diagram here, you're going to have a different radial effect than if you hit here. This might be like further into your plasma, where this might be not as far into your plasma, depending on where you actually hit your stability diagram. Generally, though, if we're speaking of like just how much the ELM itself actually impacts the core, you might be able to see something like that in these shots. So this doesn't show the ELM, right? This shows pellets and the pellet timing. But you can see that there's already in the core, like halfway through the plasma or back here, there's a big range of what the actual densities that we achieve are. And part of the reason for this range is that if you drop your pedestal, right, your pedestal drops from here to here, if you didn't drop your core as well, then you'd have like another pedestal that goes up like this, right? And that is unphysical. You'll have really sharp gradient here. So really, when you drop your pedestal, you're also dropping a lot of your core plasmas as well. And as you move farther into the core, maybe there's not as much drop, but definitely like in the range of like halfway through, you still see a big drop correlated with the ELMs.
Gotcha, that makes sense. Okay, and one last very quick question.
So
yeah, does a single, so, you know, we've talked about the stability boundary, and, you know, once you cross over the peeling ballooning, that boundary, you know, you have an ELM crash, and you're brought back into the stable region, and then you can build up your gradients again. Does a single ELM crash definitively take you out of H mode? Or do you transition into ELM mode every ELM, or?
So in general, no. In general, you'll stay in H mode. And what I mean by that is you'll continue to have a pedestal region. So you can see in this ELM crash, from like the top of this error bar basically to the bottom of this error bar, you still have a pedestal. And so you're still in H mode. It's just like a decrease in your H mode. There are examples of really big ELM dropping you out of H mode, or really big ELM triggering like a magnetic island inside your plasma, and thus leading to a disruption. So really big ELMs can have like permanent changes in your plasma, but on the whole, most of the time, if you just have an ELM, you'll still remain in H mode. It'll just be a slightly not as good H mode for a little bit. And I guess one thing I can say too is like the cycle of these ELMs can range anywhere from one ELM every like 5 or 6 milliseconds to one ELM every like 50 milliseconds or 100 milliseconds. And so there's a big range depending on like the parameters you go on and how long it takes to recover your pedestal, and how long you stay in like your most goodest H mode regime.
Okay, thanks a lot.
Yeah, of course.
Thank you for your participation. Now I will, Michael Hanson will ask the last question.
Hey, thanks, Oak, for the talk.
Yeah.
I just had a question about the RMP ELM suppression. So you can see like the drop in the D alpha, you know, so it doesn't look like there's any ELMs, or there's like a reduced frequency of the ELMs. So I guess I'm curious on how the RMP, like you're stopping these ELMs for the most part, but how is the energy still escaping to prevent that buildup?
Right. Yeah, of course. So it's escaping through the same way that it escapes in other ELM-free regimes, broadly speaking, meaning that you have additional transport through your pedestal. The cause of this additional transport in this case is a little different. It's due to the asymmetric 3D magnetic fields, which allow the plasma to have additional transport through the edge. And a big smoking gun of this, as I mentioned before, but I don't have in the slides, is that with RMP ELM suppression, you have density pump out. And so you have additional density transport that prevents your plasma from growing up to the same density values that you could have achieved earlier. So you have a less good plasma in terms of just absolute performance. But because you're preventing your density from growing up due to the 3D magnetic fields, you don't actually reach that final boundary again.
Okay, thank you.
Yeah, of course.
Okay, so once again, I want to thank you all for your participation and to thank also Oak for one beautiful and very interesting presentation. Now we will leave the room open for some extra questions, but I will finish now the recording, and yeah, thank you all for coming by.
Thank you very much for having me.